Okay, so let's talk a little bit about the concepts, and then we'll talk about some cool examples with spectroscopy. Okay, so psi approaches zero at large displacement. And so what does that mean? Well, if I have a really wide-looking potential energy well, okay, then my psi function is really spread out, right? But if I have a really narrow potential energy well, then my psi function is going to have a much larger amplitude, okay? And the width of this well is given by my displacement scale. In other words, the oscillator frequency and the reduced mass, okay? So psi approaches zero more rapidly for large masses and large force constants, so stiff springs. And so what that means more rapidly is, as it turns out, this picture that I've drawn right here is a stiffer spring. Okay, so if I go back to this picture where this is oscillating, a stiffer spring would have an oscillation that looks like this, whereas a less stiff spring would have, a slower oscillation. And so what that means, the psi approaches zero more rapidly. So that means the wave function is falling up and down a lot more chaotically than some smooth, spread out wave function. Okay. So as nu increases, the Hermite polynomials become larger at large displacements. And what that means is psi spreads out over larger areas. So this is, more or less just kind of saying the same thing, but in different ways. And then finally, as nu approaches infinity, psi squared increases at the turning points. And this is another brilliant example of quantum mechanics converging to classical mechanics via the correspondence principle. And so the idea of this, here you can see what wave functions look like for 0, 1, 2, 3, 4. Well, what about 20? Okay, so I have to draw my potential energy diagram upside down, right? So my potential energy diagram would look upside down like this, all right? And so what this is showing, as nu approaches infinity, the peak of those wave functions is getting pushed further and further out. And now if we think about just a classical spring, two masses on a spring that can displace a really large distance, if you looked at how much time each of those masses are spending at whatever position they're at, okay, for a large, classical spring, as it expands out, it's decelerating, right? The spring is starting to apply this force constant, so it's slowing down. And for a very, very brief instant in time, it's stationary before it recoils and accelerates back to some compressed position before expanding out and then recoiling. And so what that means classically, a spring is going to look like this, where it's spending most of its time out on the turning points, okay? Quantum, on the other hand, would tell us that the most likely place of finding that oscillator is, in this compressed mode, okay? So again, this is just where the classical mechanics world evolves out of the quantum world as we build up larger quantum numbers, masses, and energies.